Let's talk about the structural isomers. So, the carbon chains that have the same molecular formula but different structures are called structural isomers. There are 6 types of structural isomers. First, the chain isomers, position isomers, functional group isomers, metamerism isomers, tautomerism, and the ring chain isomers. What are structural isomers? Organic compounds all have a carbon based on skeleton or backbone. For example, this 5-carbon chain. So, carbon is the basis of organic compounds bonded to other common elements, such as hydrogen, oxygen, sulfur, and nitrogen. Since carbon can form 4 bonds, carbon atoms can combine together in a variety of ways, forming many compounds. For example, these 5 carbon molecules has 12 hydrogens. This is the structural formula of this compound. And now, what is the molecular formula? So, how many carbon in that compound? So, there are 5 carbon. So, C5, and the hydrogens has 4. So, H12. So, this is now the molecular formula. The name of this compound is pentane or N-pentane. The N indicating that it is a straight chain alkane, and the N indicates that there are only single bonds between the carbon atoms, so the molecules is fully saturated, and the pen indicate that there are 5 carbon atoms. We said that because of carbon atoms can form 4 bonds, they can arrange themselves in a variety of ways, forming many compounds. Because of this ability, compounds with the same molecular formula can form different structures.
Chain isomerism is defined as 2 or more compounds having the same molecular formula but different numbers of carbon in main chain. Chain isomers occur when the location of carbon atoms in a chain are arranged differently. This could be due to the placement of branches or length and number of branches. This results in a different structural shape. Chain isomerism example. The example is called alkaline. It has 5 carbon atoms, making it a pentane. The formula of pentane is C5 because it has 5 carbons, and if we fill each other available bonds with hydrogens, then we will have H12. Now, we have second molecules, also has 5 carbon atoms. Its formula would also be C5, and when we also fill available bond with hydrogen, we will have H12. The formula exact the same, but the structure is different. The first example is a straight chain, and the second molecule would not be called pentane because the longest single chain actually composed of 4 carbon atoms. The fifth one is a branch that connects to one carbon. It is called second carbon atom. This molecule would be called 2-methylbutane. The atoms within the molecules have been arranged differently. The longest chain of the third molecules has 3 carbon atoms made up of propane. So that third molecule would be 2,2-dimethylpropane.
These 3 compounds or molecules have the same number of atoms of each element, 5 carbons and 12 hydrogens, but their atoms are connected to each other. Note that the structure of 2-methylbutane can be represented on paper in several different ways, with the methyl group at the bottom or shifted onto the right or on the top in this position or on the top in this position. The base chain can even drawn in sort of bend or a curved structure. All of these variants represent the same compound 2-methylbutane. Remember that in reality, single bonds can rotate and chain-like molecules can be bent to a certain degree. We need to be careful when looking at the structural formulas and identify whether they represent the same structural formula, just represented differently or in a different orientation. The second type of structural isomers is the positional isomers. The positional isomers are molecules with the same molecular formula and functional groups, but the functional groups have a different position in the carbon chain. Here is an example. This is but2-ene. The ene tells us there is a carbon-carbon double bond, and the but telling us there are 4 carbons in a chain, and the 2 indicating that there are double bonds start on the carbon number 2. So, this take another example. Let's try to answer. But because there are 4 carbon in a chain. And the one is the carbon, the double bond starts on the carbon number 1. So the in is there are a carbon double bond also. So the answer is this, the but 1 in. Here the another example of positional isomerism. So is seen in cyclic or ring-like carbon structures. The structure is 1,2-dibromomensine. But we can put the bromine on the different carbon atom, give a different positional isomer. It's like this. This is the 1,2-dibromomensine. So if we can change that, this will be the 1,3-dibromomensine. So here's the another example. So let's try to answer it. The bromine is in the top. So 1. The other bromine has in the 1, 2, 3, 4. The carbon number 4. So for 1,4-dibromomensine. This is the final answer. The 1,4-dibromomensine. Functional isomers, also known as functional group isomers, are molecules or compounds with the same molecular formula but different functional groups. Here is an example of 2 functional isomers. The first molecule is propanol. The L is indicating that there is an aldehyde functional group on this 3 carbon chain indicated by prop. And the second molecule is propanol. The one here is the suffix indicating that is a ketone functional group. And again, we have a 3 carbon chain. Both these functional isomers have a molecular formula of C3, H6, and O. But their atoms are arranged in a different way, giving a different functional group. So far, we have seen that chain isomers have the same molecular formula but a different arrangement of carbons. Positional isomers have the same molecular formula but the functional group has a different position in the carbon chain. And functional isomers have the same molecular formula, has each other, but a different functional group to each other.
Metamerism, when different alkali groups are attached to the same functional group.
Now what is alkyl group? Consider methane CH4. When methane lose one hydrogen, this CH3 is known as methyl or alkyl. Similarly, when ethane lose one hydrogen, this C2H5 is called ethyl. Thus remember that when alkane lose one hydrogen, it is known as alkyl and it is represented by R dash. Now we know that this O is the functional group of the ether. Now consider this organic compound. Here, the functional group of ether is present, so this organic compound is the ether. Personally, I say that this is the left side of the ether and this is the right side of the ether. At the left side of the ether, there is one ethyl, while at the right side of the ether, there is also one ethyl. So we say that there are 2 ethyls or diethyl present in this ether. So the name of this ether is diethyl ether. Now listen carefully. I am interested to shift this alkyl from the left side to the right side. Let me repeat it. I am interested to shift this alkyl from the left side to the right side. While shifting this alkyl, give one hydrogen to this CH2 to complete its valency. Because my student also did blunder during exam while shifting this alkyl from the left side to the right side. So be careful about fulfilling the valency of this carbon. Now this is the left side of the ether and this is the right side of the ether. We can see that at the left side there is only one methyl, while at the right side there is propyl. So the name of this ether is methyl propyl ether. Note it down that I do not change the position of functional group of the ether, I only change the alkyl group. So this is one metamer, this is the second metamer. Thus remember that when different alkyl groups are attached to the same functional group, this phenomena is called metamerism. Now let me teach you one important question. Find the possible metamers of this amine. Well, this is the left side of this amine and this is the right side of this amine. At the left side, there is one ethyl, while at the right side, there is also one ethyl. So the name of this amine is dimethylamine. Now I will shift one alkyl from the left side. Also remember that when we shift alkyl from the left side, we give one hydrogen to this carbon in order to complete its valency. I get this amine. Thus this is the second metamer of this amine. This is the left side of this amine and this is the right side of this amine. We can see that at the left side there is only one methyl present, while at the right side there is one propyl present. So the name of this amine is methylpropylamine. Thirdly, I can change the position of this propyl. So I get third metamer of this amine. The name of this amine is isopropylmethylamine. Thus these are the possible metamers of this amine. Therefore remember that metamers arises when different alkyl groups are attached to the same functional group.
Tautomerism is the type of isomerism which arises due to shifting of proton within a molecule.
In this video, we're going to talk about a process called keto-enol tautomerism. It's kind of a mouthful to say that. This is basically the interchange of a ketone, or in some cases an aldehyde, to a new sort of functional group called an enol. So let me just draw out the basic type of reaction I'm talking about here. So I'm going to call this the keto form because it has a C double bond O. It turns out that these can undergo a process that converts the keto into what's called an enol. And the reason this is called an enol group is, notice it's got an alkene and an alcohol. So we add those two together, we get an enol. This process of going back and forth between the two is called tautomerism. And it is a reversible process. Now, why does this happen? Might be the next question. Well, it turns out that carbonyls, because they are a fairly polar group and the carbon is partially positive charged, it turns out that if you have hydrogens next door to a carbonyl, and in this case I'm just drawing out the hydrogens, these particular hydrogens are called alpha hydrogens. Okay, so when you're talking about carbonyl nomenclature, if you go one carbon away from the carbonyl, that's called the alpha carbon. And in this case, this alpha carbon has hydrogen, so they're called the alpha hydrogens. These are mildly acidic. So when you dissolve these into water or put them under acid or base conditions, these protons can potentially come off. And if they do so, what they form is something like this. This is called an enolate. So what happens is that in solution, there's proton exchanges that can go on back and forth that allow a ketone to be converted into the enol and vice versa. And again, the reason for that is because of the presence of these acidic alpha hydrogens. Now it turns out, in reality, the keto form in most cases is going to be the favored form of these. So if I were to look at an example of a ketone, let's look at acetone. And let's draw out what its enol would look like if it were to form. Okay, so this is the enol form. I just mentioned that the keto form is typically the more favored form. So if we actually were to measure the relative amounts of these, this one would come out to be about 99.99%, whereas this one would be 0.001%. So it's a very, very minor amount that would ever go to the enol, particularly with ketones. However, when you talk about aldehydes, let's look at the example acetaldehyde. Okay, so this is acetaldehyde. Notice that acetaldehyde does have acidic alpha hydrogens. This is an alpha carbon. It has these methyl hydrogens attached in an alpha position. So if we were to form an enol of this, the enol would look like this. Now, this, even though it's called an aldehyde, in this context of tautomerism, this would be called the keto form, and this would be called the enol form. In the case of aldehydes, the percentage actually is a little bit higher for the enol. So we get about 0.1% of the enol, which is considerably higher than in the case with the ketone. So as we'll see in the next section of the video, it turns out if you have a mixture of aldehydes, they can undergo a very special reaction because of this keto-enol tautomerism.
Ring chain is a compound have same molecular formula. but one has an open chain while the other have cyclic structure are called ring chain isomers.
So here's the example of ring chain isomers, the C4H6. So let's construct the structure. So structure number 1 will be the CH3 single bond, C triple bond, C single bond, and CH3. So it is the 2-butane. So structure number 2 will be CH2 double bond, CH single bond, CH double bond, and CH2. So these two will be the open chain isomers. So the structure number 3, it is the cyclobutane. So how we can formulate or construct here the CH, this is the double bond, CH, CH2, and CH2. So how many C4 and H6? So 1, 2, 3, 4. 4 C4. So H 1, 2, 3, 4, 5, 6. So H6. So let's construct the structure 4. Here is the cyclopropane. Here's the cyclopropane or 2-methyl cyclopropane. CH3, this is the double bond, CH and CH. So now this is the functional isomers, and these two also the ring chain isomers. So we said having a same molecular formula but different mode of linkage, open or closed chain, all the ring chain isomers are functional isomers, but all functional group isomers are not ring chain isomers.